Hello everybody, welcome back to another discussion dynamics. Today we will start a new topic. We will start kinematics of rigid bodies and we will focus on velocity analysis. And plan for today's following, we will start with a very brief lecture review and then we will do two examples. Without further ado, let's dive straight into our discussion. Here is my brief lecture review. So today, for the first time, we will not talk about particles, but we will talk about rigid bodies. So let's assume that we have a rigid body of an arbitrary shape. So this is rigid body. And we can specify 2 points on that rigid body. Let's say point A and let's say point B. And let's assume that we know velocity at point A. So we know this vector. And we also know omega of the body. And naturally, we know the geometry. So we know this vector that connects point A and point B. I will call it RBA. So these are our knowns. And what we would like to find is this vector. I would like to find velocity B. This is not known. And in order to do it, we should just go for this equation. VB is VA plus omega body times RBA, of course, vectors. All right, this is actually the end of my lecture review. We will use this equation today 5 times. Any questions?
So when we say like B relative to A, does that mean the vector, like it goes from A to B?
Yes. Yeah. Joey. So yeah, that's true. Basically, this vector is RAB. Right? The opposite vector, yeah. So RBA is minus RAB. Exactly. Any other question? I don't see any. So example number 1. As usually, please take a couple of seconds to read and understand the problem statement before we start our solution. Okay, this problem statement is quite short, so I think I can start solution. So what do we have in here? We have our rigid body, which is a wheel in this case. We know that at point A there is no slip. So maybe one of you can tell me what is the velocity at point A? It's 0, exactly, because our ground is stationary. Our ground does not move. That's why our point A has exactly the same velocity as ground, yes, which is 0. What else do we know? We know geometry, and by saying that I mean that we know diameter of the wheel, and we also know that our omega is 15 revolutions per second. What they ask us for is to find velocity at this orange point, velocity at wheel's center. Okay, so let's see what we know. We first of all know that velocity A is 0. And then I think that they provided us omega and diameter in units that are a little bit useless for us. So we should probably convert them into those that are useful for us. So let's start with omega. Omega is given as 15 revolutions per second. And I believe that we should convert it into 15 2 pi radians per second, which is exactly equal to 30 pi radians per second. How about diameter? Diameter is given in inches, but I prefer feet. So this will be 3 feet. And instead of diameter, I prefer to have radius. So this implies that our radius is exactly 1.5 feet. Okay, and here is our solution. So we have our wheel. We know that velocity at point A is 0. We know that our omega rotates in this direction. And they ask us to find velocity at this point. Okay, so let's go for the equation from the previous board. In here we have, we will have Vc that is equal to Va plus omega times Rca. So our Vc will be equal to 0, 0, 0 plus 0, 0 omega. But that omega, question to you guys, does that omega rotate in a positive fashion or negative fashion? In other words, is that omega pointing into the board or out of the board? Anybody? It is into the board, yeah. So it will be minus omega, right? So in here I have to write minus omega. And I have to cross it with this vector, but that vector is not yet on the picture. Let me draw it first. RCA is here. Okay, so I think that components of RCA are 0, R0. Yeah, and so in order to solve that problem, we have to solve this determinant. I, J, K, 0, 0 minus omega, 0, R0. Let's do it quickly. This would be omega R. This is 0. And this is 0. Great. So our Vc is 30 pi times 1.5, 0, 0. If you grab your calculators, you will obtain that this is exactly 141.3700 feet per second. Yeah, and this is our answer. So you can just express our answer using either my favorite notation, which is already on the board, so I will just rewrite it. Or if you prefer, you can also express it in such form. Okay, this is the end of example number 1. Any questions? I don't see any questions. Okay, so what? Example number 2? Let's do it. As usually, please read it, understand the problem statement before we start our solution. No worries. Okay, so what do we have in here? I think that we have a very similar situation to what we had earlier, just different things are known and they ask us to find a little bit different things. But the methodology will be exactly the same. Okay, so what do we know? I believe that definitely we know radius. I'm pretty sure that we know that velocity at point O is 0. Velocity O is 0 because there is no slip in here. And also we know that velocity C is horizontal. So VC is VC 0, 0. Okay, and they ask us to find 4 things. They ask us to find omega and velocities at points A, B, and D. So let me create such table. So this is what they ask us to find. Omega, velocity at point A, velocity at point B, and velocity at point D. All right, here is my solution. I will start with some auxiliary drawing. So this is our circle. Let's say that this is point O. So we know that velocity at point O is 0. We also know that the velocity at point C is VC. And let's assume that our omega rotates in a positive fashion, okay? Let's assume that our omega rotates in this way. And let's find omega. So I just would like to write our velocity expression between points C and O. So it will look like that. VC is equal to VO plus omega times RCO. We know that VO is 0, so we can set it to 0. Vector. And our VC will have following expression. 0, 0 omega, since I assumed that omega is positive, times this vector. Aha, I must draw this vector first. This is RCO. And this will be 0, R0. Okay, determinant. 0, 0 omega, 0, R0. Let's solve it. Minus omega R, 0, 0. Great. And I will replace VC with what we see at the top of the board, okay? Because our VC has only one component. VC 0, 0. Okay, so we ended up with VC 0, 0. That is equal to minus omega R 0, 0. Okay, so we ended up with 3 equations, yes? But 2 of them are tautology. equations for the y components and z components are trivial. Yeah, and the only one that is useful for us is the one in the x component. So in here we can write that our Vc is equal to minus omega r, which implies that our omega is equal to minus VCR. And again, if you want, you can write it vector-wise. Our omega vector is 0, 0 minus Vc divided by R. Or if you prefer US notation, you can write minus VCR K. Okay, I think that 25% of the problem done, right? Any questions? Okay, so before continuing the problem, I will just fill out our table. 0, 0 minus VCR. Okay, and now I would like to continue with maybe finding velocity at point B. Okay, so I just want to find this velocity at this point. So in order to do that, we can write down equation between, I don't know, B and O. Is it fine? We can also write equation between B and C, and we will obtain exactly the same answer. However, I prefer to write it between B and O. So let's do now between B and O. At home, you can do it. At home, you can try doing it between B and C if you want, and you should obtain exactly the same answer. But anyway, VB is equal to VO plus omega times RBO. Again, our VO is 0. And our VB has following expression. VB is equal to 0, 0 minus VC divided by R times this vector. Let me draw it first. I think that RBO is here. This is RBO. And its components are 0 to R0. Determinant. I assume that you know how to solve such determinants. Oops. So this will be 2VC 0, 0. Okay, we found our VB. As you can see, this vector will be twice longer than VC. So our VB will be here. This is our VB. Oops. Can I draw a horizontal line or not? Okay, there it is. This is VB. Any questions? Yeah, you see the concept here, yes? Our steps are quite repetitive, yes? We can follow the recipe. Okay, so let me fill this out. And let's find VA and VD, okay? And this will be probably the end of our today's discussion. So let's do it quickly. I think that in this drawing we have already too many vectors. Let me draw a new drawing, okay? So we know that this is our circle. I can do a better circle. We know that velocity of this point is 0. And where was point A? Let me scroll the board. Aha, point A is here on the right-hand side. So again, I hope you don't mind that I am going to again write equation between A and O. Between A and O. And it will look like that. VA is equal to VO plus omega times RAO. Okay, so our VA is equal to, this is 0. Our VA is again equal to 0, 0 minus VC divided by R times this vector. This one is RAO. And this is point A. So maybe one of you would like to join the discussion. Do you want to tell me what are the coordinates of this vector, of that blue vector? Anybody? James.
R0.
Perfect. Exactly. R0. Okay, determinant 0, 0 minus VC divided by R, RR0, and this will be VC minus VC and 0. Okay, so our velocity at A will look like that. Yep. As you can see, this is right angle here. Our vector VA forms right angle with vector RAO. And this is because velocity of point O is 0. Velocity point O is so-called instantaneous center of rotation. That's why this angle is 90 degrees. That's why this angle is 90 degrees. If the velocity of point O were not 0, that angle would not be 90 degrees, yes? We will talk about instantaneous center of rotation later this semester, okay? Just a heads up. Okay, so let me scroll up the board and fill out our table. VC minus VC 0. Okay, so we have just one last thing left. Yes, finding velocity of point D. So actually, in my previous discussion, there was one student who had a great idea. He said that that it would be very educational if we find velocity of point D, which is here, in two ways. Let's solve it twice, okay? First time, let's solve it between point D and O. And second time, let's solve it, I don't know, between D and A. And I promise you that we will obtain exactly the same answer, okay? So let's do it between D and A. It will show you that you are free to choose whichever 2 points you want in order to solve velocity analysis, okay? So let's do it quickly. VD is equal to VO plus omega times RDO. Again, this guy is 0, vector. So this will be this is exactly what you've seen already, times this vector, and I bet that all of you know that this vector is here. This is RDO. And its components are minus R, R0. Okay, determinant. And if you solve this determinant, you will obtain that our velocity vector is VC, VC, and 0. Let's draw it quickly. That vector is here. This is our velocity at point D. And again, you can see that it's perpendicular to our orange vector. Okay, and the last thing today, let's do exactly the same, but this time between these 2 points. So in here we will have VD is equal to VA plus omega times R dA. So our VD is equal to, what was VA? Aha, VA is found here in the top left corner, top right corner, sorry. VA is VC minus VC0. Omega is unchanged for the body, so it will be 0, 0 minus VCR. And now this vector. I think I'm gonna use green ink to draw it. RDA is here. This is RDA. So this will be minus 2R, 0, 0. Yeah, this is a horizontal vector. Okay, let's solve that determinant, but on the side. So this determinant is IJK 0, 0 minus VC divided by R minus 2R 0, 0. Zero here, 2 VC in here, and 0 in here. Okay, let's add these two vectors to each other. So in here we will have VC. In here we will have minus VC plus 2 VC. And this is 0. So we will end up with VC, VC, and 0. Exactly the same answer we obtained earlier. Yes, this one is exactly the same as this one. Okay, this is the end of the discussion actually. Are there any questions? Is it easy? Yeah, okay, cool. So what do you learn today, guys? You learned the velocity equation, yes? The equation you can use in velocity analysis. Wait a second, I have like can I take 60 seconds of your time? Yeah, I want to summarize it. So you learned that equation, then you learned that you are free to choose whichever pair of points you want. You will obtain exactly the same answer, yes? And the third thing you learned today is that this is kind of repetitive, yes? This is kind of automatic thing to do. So basically, I think that the purpose of this discussion is to show you, first of all, how to run velocity analysis, and second of all, it was to show you that this can be automatized, yes? So basically, in the future, if you decide to continue your engineering, engineering journey, if you decide to learn more about dynamics, you will probably learn certain softwares that are used in industry, yes? And these softwares will do that for you automatically, yes? Because this is why we have computers for, yes? We don't want to do very dull stuff. We don't want to do very repetitive stuff. Yeah, this is what we have our computers for. So I think that the purpose of this discussion was to just show you what will happen behind the scene, what happens behind the scene when you use industrial software, yes? Okay, and with that positive information, thank you for today and see you Friday. Bye-bye.